So so and then I find there are some empty seats here. Okay, but uh, so uh, actually I have found some trend. So actually at the beginning of the semester, the class is full. The classroom is full, but after the midterm exam, then I can find many empty seats after the midterm exam. And then the number of students in the classroom decreased continuously until the final. But uh, actually, you may think you may think that the the time is not enough for the midterm exam, but it's my intention. Okay, so I believe the number of questions is rather it's a rather large. Okay, but uh, if you can answer all questions within the exam time, then it's very brilliant. Okay. Okay. So don't worry, and then uh, please do your best until the final exam. Usually, you can make up your score in the final exam. Uh, and then I posted the exam score on LMS. So can you find it? No, no. Oh, really? So the the LMS system was changed. Okay, right? So actually, I cannot find any exam score on LMS. So I created the assignment score for the midterm exam, and then I posted the your midterm exam score on LMS. But if you cannot find, so I will check it. I'll check it later. So and then also another announcement. So the the next class is on May 1st. So and then it's Labor Day. Uh, Actually, we don't need to observe the Labor Day because you are students. Okay, but anyway, so uh, you you can take a rest actually. So we will not have a class on May 1st. So on observance of Labor Day, but I will record the lectures, and then I will post the lecture uh, on YouTube. So anyway, so also unfortunately, so the May 6th is the also it's a kind of national holiday, right? So because it's a Buddha's birthday in May, right? So 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 we cannot have a class on May 6th. So we will have, so you can take a rest for 1 week, but so we need to make up the class, right? Because so we need to have the a fixed number of classes, and then unfortunately, the June 3rd is the National Vote Day, so we cannot have a class, and then also so I need to attend the conference after uh, near the I believe it's around the early June. So uh, but we need to make the class. So I will record the video. So and then I plan to record the one video during the this weekend, and then so I will also record the makeup lectures for the our missed classes. Okay. So so we will not have classes on May 1st and then May 6th, right? Okay, and then, but so so I will also post the lab assignment today. Okay, and then so actually, so we are learning about the processor architecture. And then so and then so you can understand how to organize this hardware architecture of CPU by designing your own processor. So that's why. So we have the design labs for this course. So, just the assignment. So you can, I believe you can easily follow the lab assignment. Okay. So because so actually the so it's a fourth lab assignment, right? So so in the fourth lab assignment, so you will be requested to design data path element. So what are data path elements? So we learned in the previous class, right? So in the CPU design, CPU hardware, data path element represent the elements that process data and addresses, right? So it receives the data or data path element receives data input. So it means it's kind of the, the meaningful data such as addresses, also the program counter. So we can start from the program counter actually. So program counter is the address of an instruction, right? It's address. Also instructions. So instruction, as I mentioned, the instructions are data, the data in memory. So a processor read instructions from the instruction memory, and then we use program counter as an address, and then these instructions are decoded and executed by other components such as the ALU. Also we can access our data memory. Also we can access register file, right? So these are data path element. So, and then actually in the previous class, we learned about the instruction memory, register file, ALU, and data memory, right? So in this fourth lab assignment, so you will be requested to design these data path element, right? So, and then actually, so firstly, so this is the example. So actually, I I already showed the example of this database element, right? So this is the program counter, and then this is the instruction memory. Okay, so actually, if you see that this what happened? So this figure, so you can find that uh, this database element, for example, instruction memory includes the read port and then output ports. So it receives the read data from the read port, and then it processes this input data, right? So input data is a PC, right? And then it creates output data, right? Output data is an instruction, right? So we can, so this is a program counter actually. So I already explained about the, the behavior model of instruction memory, right? So it received the program counter as an address, right? And then it just create the data out. So data out is on stored instructions, right? So you can just complete the design of this data path element. So you will be requested to design uh, instruction memory, register file, ALU, and uh, data memory, right? But I will provide the skeleton code. And so which means this skeleton code will include the input and output ports. Also, I will provide the test bench, right? So you don't need to design your own test bench code, okay? So, but you need to compile your design module and then test bench module with equals value, and then you can run the test bench module, right? So this is the fourth lab assignment, okay? So we learned how to design and how to design each part of a single cycle processor. Okay, so I believe we can just learn until this part. Okay, so and then we learned how to design each database element, and then we can just connect the first. So in the previous class, I explained how instructions are processed by these database element. So, and then, these database elements are just a block, right? Blocks, right? And then these, these blocks or these modules, as I mentioned, receive the data, like, right? Data from input port, and then it generates the output, right? And then these modules perform the required processing for executing instructions, right? So the output is generated, and then these output from one database element can be used by other database element, right? So this is the example. So register file so provides the output data stored in the register, and then we can use the read register number one and read register number two to index the target data in register file, and then the register file uh, provides the requested data, right? And then this data this data is provided to the ALU. So that means ALU will use the output from register file as the input of ALU, right? So we can connect the output and input of ALU, right? So also you can find the arrow here. So it means that the data flows from this port to this input port of ALU. So data flows this direction. Okay. So we can connect the input and output ports of data path element. So we can build the entire CPU design. So it means the single cycle CPU, right? So and then also uh we need to consider some different cases. For example, ALU. So ALU can receive data from registers, right? For example, if we just perform add x1, x2, x3, right? So ALU receives operands from two operands from the register file, and then it generates the result. But we can also implement the immediate instructions like add I, x1, x2, immediate. So what does that mean? The ALU needs to receive one operand from immediate value. So where is this immediate value? The immediate value is included in the instruction. So we also learned about the immediate generator, right? So as you can see, immediate generator receives the instruction, and then it generates the immediate value, right? So ALU can receive the data from register file or immediate value, right? So there are two cases. So we can use multiplexer, right? So two inputs, and then we can select one data from two inputs. Then we can use a multiplexer, obviously, right? So multiplexer receives two inputs, and then using this selection control input, right? This is the control signal. And then we can select the one of inputs to the output of a multiplexer, right? So Multiplexer includes the selection port. And then this is the control signal, right? So control signal control the behavior, the behavior of this multiplexer, which means if the ALU source is zero, right? Zero, then this input, this input is selected. So what is this input? This is the data from register file. And if the ALU source is 1, so you can find the 1 here, right? Then this multiplexer selects this input, right? This is the output from immediate generator, right? Then ALU can receive the immediate value. So if if we need to select a certain if we need to select the one data from multiple data, right? So then we need to use a multiplexer in this case, right? And then we need to control this multiplexer with the control signal. So in this case, the control signal is the ALU source, right? So this is the full data path. Okay, this full data path. So we just connect the data path element, but we do not connect the control port here, right? So also you can find some multiplexers here. So here and here and here. Okay. So then, so in order to build the complete design of this single cycle processor, then we just connect. We design the data path elements, right? And then we connect the input and output ports of this data path element. And then if a certain data path element require the multiple inputs, then we need to select the one data from the multiple inputs. So in this case, we can add the multiplexers, right? So then we need to connect the control signals. So as I mentioned, the control signals change the operation mode of the data path elements, right? So for example, multiplexer, so as I mentioned, so this ALU source, so this is the selection signal. This selection signal changes the operation mode, right? So it means we can select this input or this input as the output of multiplexer. So a CPU, also the most digital design needs to have control signals, right? So we need to control the operation mode of the data path element. So we require control unit, right? And then as you can see, control unit receives instruction, right? It receives the instruction. So it is because the behavior of this CPU is determined by obviously instructions, right? The CPU generate the different operation, different types of output based on the instructions. So the control unit receives instruction, and then it generates the control signals. So in this example, the control unit generate the regulate signal also. So ALU source, and then ALU operation signal, and then so mem read and mem write, and then branch signal, right? Because the CPU uh, runs with the different operation mode by instructions, right? Then how can we generate this control signal? Firstly, let's learn about the ALU operation because so the ALU operation is so the ALU need to support the many different types of instructions, right? So uh so as you can see, our CPU is the simplified version, right? So so we are learning about the RISC-V CPU, but in chapter 4, we are learning about the CPU that support only the limited number of instructions, right? Our CPU will support load word and so store word and add sub and or instruction and then BQ instructions. And actually, the ALU needs to generate output data for these instructions. So ALU needs to support various operations, so various processing mode. Okay, so let's see. So so ALU used for load and store instructions, right? So which means, so as I mentioned, our CPU needs to support the load word and store word. Then you need to figure out the required operations for this ALU. So, for example, the load word x1, x2, and actually the load word is represented like this, right? So this is the load word instruction. So actually this is the destination register, right? And then this is the immediate value, and then this is the source register. And then what is the behavior of this load word instruction? We just generate the target address to data memory, right? So we need to perform add operations using source register and immediate value, right? So which operation is required? Add. Stored is the same, right? In order to generate the target address, the store word needs to perform add operations using immediate value and source register. So if the instruction is memory instructions, right, then ALU needs to perform add operation. How about the branch? So we just support the BEQ, right? But other branch instructions such as BNE and BLT and then BGE. So actually, we need to compare. We need to compare two operands for branch instructions, right? And then in order to compare two number data, then we can just perform A minus B, right? It's A minus B is 0, then we need to check the BQ, and if not 0, then we can check B and E. And then if the A minus B is less than 0, then we can check the BLT, right? And then A minus B is 0 or greater than 0, then we can check the BGE, right? So for the branch instructions, we need the ALU. ALU needs to perform subtraction because we need to compare two values, right? Obviously, and the R type. So R type instructions were immediate, so some arithmetic or logical operations. So ALU needs to perform various arithmetic or logical operations. For example, our CPU needs to support the AND or add subtract, right? The ALU need to support these operations, right? So for the R type, for example, also for R type instructions, the ALU needs to support these four different instructions. But you can find that in this example, ALU control signal is 4 byte. But ALU just need to support the four different instructions. So you can find that the number of bits for ALU control is redundantly large, right? So it is because, so actually the original RISC-V CPU need to support many other arithmetic or logical instructions, right? But this is the simplified version. So we just support the four different instructions using ALU. But original RISC-V needs to support the many other the arithmetic or logical instructions. So that's why ALU control bit includes 4 bits. Okay. So and then actually, so we can use this ALU control bit for identifying the operation mode of ALU. So for example, if the ALU control bit is 0000, then ALU will perform add operation. So which means ALU receives two number data, and then it performs add operation, and then it will generate the output, the result of addition, right? So this is the summary of ALU operation, right? So, and then in order to generate the ALU control signal, then we firstly generate the ALU OP field, no, ALU OP signal, and then we generate this ALU control signal. So it looks like this. So this is the instruction. Instruction is given to the ALU OP generator. This is control unit, and then it generates the ALU OP signal. ALU OP. So this is the 2-bit signal. And it is given to the ALU control generator. So, and then this ALU control signal generate the 4-bit ALU control signal. Okay. And then also the part of instruction is given to the ALU control. So it is because, so think about this. So this is the summarized the instruction table in the RISC-V IV32I. But if you see this table, then you can find that OP code identifies the type of instruction. What does that mean? If you check the OP code field, so we can identify, you can figure out that, oh, this instruction is load instructions. Or if we can check the also OP code, and the OP code is 010011, we can figure out that, oh, this instruction is store type instructions, right? So actually, if we firstly check this OP code field, we can figure out the instruction type, right? So, and then when I explained about the operation of ALU, then also I classify the operation mode like this. For example, if the instructions are load or store instructions, these are memory type instructions, right? Then ALU just performs add operations, right? And then if the instruction type is a branch type, then ALU just performs subtraction only, right? And then other type instructions such as arithmetic or logical instructions, ALU performs the ALU actually performs the various operations, right? Based on function 7 and function 3 field, right? So that's why we firstly define the ALU operation, 2-bit ALU operation control signal first using the OP code, and we just generate the final ALU control signals by checking the this function 3 or function 7 field. Do you understand? So for example, if the OP code field is 00011 and then 010011, it means it's a load type, and then this is the store type. So these are memory type instructions, right? Then we can just generate the ALUOP 00. And then in this case, ALU just performs addition. ALU does not check the other fields, right? Right, obviously, right? ALU does not need to check other fields such as the function 3 or function 7 for this case. So firstly, we just use this set the ALU OP signal as 00, and then ALU just performs addition only. Branch is okay, the same. If the OP code field is 110011, then it means that this instruction is a branch type instruction. Then we just generate the ALU OP signal as 01, then ALU actually, so we do not check the other fields, right? The function 3 or function 7. ALU just performs subtraction. So by checking this ALU OP signal, if the ALU OP signal is 00, then AL control signal just becomes 0010. So it just supports addition. And then if the PQ instruction, if the ALU OP code field is 01, then ALU just performs subtraction. So we just, the ALU control unit just generate the 0110. And the other type instructions. So for example, so if you check this table, right? So you can find actually the shift, arithmetic, logical, and compare instructions. And then you can find that these instructions can have OP code such as the OP code field such as the 0110011. So it means the R type instructions, right? R type instruction, but it just performs arithmetic or logical operations. And then if the OP code is 0010011, right? So you can check your slide. So then it means it's the I type instructions. But as you can see, these instructions have actually the same the OP code field. So it means if the OP code field is 0110011 or 0010011, then ALU needs to support various arithmetic or logical operations, right? And then this mode is this mode. So ALUOP becomes 10. And then in this case, we need to check the function 3 or function 7 fields in order to identify the required operations for ALU, right? So but our in chapter 4, we just support the reduced number of instructions. So we just support the R type instructions, right? So if the OP code field is 0110011, then we need to check the function 3 or function 7 fields, and then we need to figure uh, figure out the ALU control signal like this. Okay, but in the lab, so uh, in the lab assignment, so we will support more instructions, right? But then you can just check the this table to generate the ALU control signal, right? Okay, so this is the summary. So actually, uh, as I mentioned, we need to check the function 7 or function 3 field if the ALU office signal is 1, 0, right? And then actually we need to check the only this bit because there are only 3 modes, right? So actually ALOP in this example, ALOP has only 3 different values, 0, 0, 0, 1, 1, 0, right? So we can only check this one bit to uh, check the behavior mode of ALU, right? So you can check this table, okay? So this is the completed data single cycle CPU design, okay? So as I mentioned, we also add the control unit. So firstly, we just define the data path element, right? We can just design the data path element, right? Each block, and then we can connect the input and output ports of data path elements. And then, as I mentioned, if we just connect the input and output ports, the data flows from output port of one data path element to the input ports of other data path elements, right? Data flows, because you can find the arrow here, right? Data flows. And each data path element includes control input, right? So we need to connect also the control signals. And then control signals are generated by control unit. But if you see this control unit, so you can find that the instruction is connected. But you can find that instruction instruction bit field from 0 to 6 to 0 is connected to control unit. So what does that mean? In our instruction, this field includes the OP code, right? And then the main control unit, so this control unit just receives OP code, right? 7-bit OP code field in an instruction. So you can find the OP code field here, right? Then we can identify the type of instructions. Then which control signals are generated? So branch, mem read, mem to reg. You can find the ALUOP here, right? So as I mentioned, we can generate the 2-bit ALUOP control signal. And then I explained that these ALUOP signals can be created based on the OP code field only, right? And then mem write, ALU source, and then reg write. Other control signals are also generated in the control unit, but based on the only OP code field, right? And then you can find the ALU OP is connected to the ALU control signal, right? And then ALU control signal, ALU control unit generate the ALU control signal. This is the 4-bit signal, right? And then as you can see, ALU control unit receives the other fields, right? Okay. So, but you can, as you can see, you can find that only the instruction bit 30 and then 14 to 12 is connected to the ALU control unit. So it is because in chapter 4, we just support the reduced number of instructions, right? That's why we need to just figure out, oh, this is the add instruction, this is the sub instruction, and this is the end instruction, this is OR instruction. Only 4 instructions. But actually, we need to check the function 7 field and then function 3 fields in ALU control unit, because the RV32I needs to support the various instructions, right? More instructions. So actually we need to check the function 3 or function 7 fields in the ALU control unit, okay? And then ALU control unit generate the 4-bit ALU control signals, right? So this is the completed design, completed the single cycle CPU design. So, and then the CPU can support actually the reduced number of instructions, as I mentioned, the load word, store word, BQ, and then add, sub, and end or instruction, right? And let's see how this CPU works. Okay, the R type instruction. So for example, R type instruction is the add x1, x2, x3. So this is the example of R type instructions, right? So let's see how this instruction is executed in this single cycle processor. Firstly, PC is set, and then using the PC. So this is the common operation, right? The PC is given, and then we can read the instruction. And then let us assume that this instruction is all type instruction. So add x1, x2, x3. So then, as I mentioned, the OP code is given to the main control unit. And then main control unit needs to generate these control signals, right? How about the branch? What is the output? Output of branch. This is the R type instruction. Branch is obviously 0. Why? Because this instruction is not a branch instruction. So then you can find that the branch control signal is connected to this AND gate, right? Then what does that mean? If the one of input of this AND gate is 1, then actually it's just same to this is connected, right? And then the output of AND gate is connected to the selection signal of this multiplexer. Then what is the purpose of this multiplexer? So we can just select from the PC plus 4 and then target of the branch, right? But this is the R type instruction, so we don't need to use this multiplexer, right? So which means it is always 0. This is not a branch instruction, right? This is R type instruction, so which means the next PC is always PC plus 4. Only this line, this input is selected by this multiplexer. And then for this operation, the selection signal is always 0. So one of input is always 0, then and output of AND gate is also always 0. So branch is actually 0. Now obviously this is not a branch instruction, so branch is 0. How about the mem read? So you can find that mem read is connected to this port, okay? So mem read becomes 1 if the data memory is read. So this is required. This is necessary for R-type instruction. No, because R-type instructions do not access data memory, right? R-type instruction just use ALU. So mem read is obviously 0. So you can just figure out the output value of a control unit like this. So this instruction does something, so some operations. Then in order to support the required operations, we need to control the operation mode of data path element, right? How about the mem? How about the mem to reg? So as you can see, mem to reg is connected to this multiplexer. So what is the purpose of this multiplexer? So you can find that this multiplexer receive output from ALU. So this is ALU result. So this is connected to this multiplexer. And then another input is connected to the read data. So this is the data output of data memory. And then also as you can find that if this signal is 1, then this line, this input is selected, right? So you can find the number 1 here. So what is the value of mem2 reg? And what is the purpose of this multiplexer? So output of this multiplexer is connected to the write data. So what does that mean? This multiplexer selects the write back data. And then the write back data can be from ALU or data memory. But this is the add instruction. So what does that mean? Add instruction just to perform the add operation by ALU, and then the result is written back to the register file. So we need to activate this input by this multiplexer, right? So do you understand? So this signal needs to be 0. So you can find the number 0 here. So if it means the mem2 reg is 0, then the ALU output. ALU output is selected as the written back data. So it is also 0. Okay. So mem2 reg. So it means memory to register, right? But it should be 0 because this input, the memory output is not selected. ALUOP. So as we learn, ALUOP becomes 1, 0. So it is defined in this table, right? So ALUOP becomes 1, 0. And how about the mem write? Obviously, this is not a store instruction, so memory is not used. Mem to write is also 0. ALU source. So if you see this ALU source, then you can find that ALU source is connected to the selection port of this multiplexer. And this is the R-type instruction. So we need to use this read out port, read out data from the register file, right? So ALU source is also 0. How about the reg write? If the reg write is 1, then which means that the write data is updated to the register. Then how about the reg write signal? So if we just analyze the behavior of this R-type instruction, then R-type instruction has the destination register, right? So destination register is updated by x1 plus x3, so IL output. So leg write needs to become 1, right? So based on the required operations for an instruction, we can define the output signals of this control unit, right? Right. And then actually we can check the OP code field, right? To understand? How about the load instruction? Like load word x1, immediate x2. Branch is a 0 because it's not a branch instruction. It's a mem to read is should be 1, right? Think about the operations, the operations of load word. So load word reads data from data memory. So we need to activate the mem read operations for data memory, obviously, right? So it's 1. Mem to read, oh, output of data memory needs to be written back to the destination register. So read data. This data output from data memory needs to be activated. So selected by this multiplexer. So it is 1, obviously. And then we already defined the AL code. So this is 00 for the memory instructions, right? And then memWrite is 0 because this is load instruction. We do not update the data memory. So we do not need to write data to the data memory, right? So memWrite is 0. AL source, what is the AL source? Load word uses immediate data. So, and then, so which means this immediate data needs to be given to the second input of ALU. So ALU source is 1, right? So, this is the multiplexer. So this is the multiplexer for the second input of ALU, right? And then actually we need to select the immediate data from immediate generator. So ALU source needs to be 1. How about the leg write? Load word, update the destination register. So leg write is also 1. So, right, like the same way, so as I analyzed the R type instruction, so we can just we can just define the control signals for other instructions, right? How about the BQ? Obviously, it's branch instruction 1. So, as I mentioned, this input, the branch control signal is connected to the one of input of AND gate. So what does that mean? If the AND gate has the 2 inputs, so if this input is 0, then it becomes 0, and then if this input becomes 1, then it becomes 1 because this is always 1, right? So what does that mean? If the branch instruction like BQ, X1, X2, and target, okay, this is the branch instruction, and then it check the equality of X1 and X2, the source registers. So you can find the 0 output here. So, and then it means it detects the zero, zero output. So it means if the ALU result is 0, then it becomes 1, right? It's a 0 detection signal. So if the ALU output is 0. Okay, ALU result is 0. Then this 0 signal becomes 1. In the BQ, and then we already learned that for the branch instruction, ALU just performs the sub instruction, right? So like X1 and X2. So it just performs the X1 minus X2, right? Which means if the X1 minus X2 is 0, then it's X1 is equal to X2, right? So 0 becomes 1, right? In this case, it becomes 1, and then the output of AND gate becomes 1, right? So by this multiplexer, this input is selected. So what is this input? This input is the PC plus immediate, the target of branch instruction, right? So the target is selected. So it means the branch is taken. So you can find that if this input becomes 1, so which means that the branch condition is true, right? Then, so if the branch condition is true, then it becomes 1, and then another input, the branch is 1, then the output of AND gate becomes 1, so this input is selected, right? But if the branch condition is false, then this input becomes 0, right? And then the output becomes 0. So this input, this input is selected. What is this input? This input is PC plus 4, right? The next instruction, not the target of branch instruction. Okay? So do you understand? Do you understand? Okay. So for a branch instruction, the control unit, the branch control signal becomes 1. And then this branch control signal works like this. Okay. Mem to read, obviously 0. It branch instructions do not access data memory. How about the memory to read? 0, 1. So think about this. So branch instructions do not update register file, right? Do not update general purpose registers. Branch instructions just update PC. Only, okay, only this data path element. So actually the branch just activates this part, this data flow, right? So actually the branch do not use this data flow. So it means it's the data flow for updating the general purpose registers. So what does that mean? Don't care. 1 is okay, 0 is okay, right? But so in this case, we can use don't care, right? And then if you took the logic design course, and then if we just set the output as a don't care, then we can simplify our design, right? We can more simplify our design more, right? So 1 is okay, 0 is okay, so it's don't care, X, right? Do you understand? Because we do not use this data path, okay? We do not use this data path. The branch instruction just to use this data path, right? This data path. So it's don't care, and then ALOP. What is ALOP? We already learned 0, 1, because the ALU needs to support the subtraction. Okay. Mem write is 0. Okay. Memory is not used, so 0. ALU source, what is ALU source? This ALU is used for comparing two operands from register file, right? BQ X1, X2. We just compare X1 and X2. So ALU source is 0, right? So ALU receives two inputs from register file for the branch instructions, right? So it's a 0. How about the reg write? So ALU source is reg write. So as I mentioned, the branch instructions do not update register file. So it's 0, right? Do you understand? So you can analyze how instructions are executed in the single cycle processor design. So firstly, we just organize the data path element, and then we define the control signals, and then we just connect the control signals generated by the main control unit. And then we can just define the output signal, output control signals from this main control unit based on the required operations for instruction types, right? So you understand? Okay. So we just check the three different types of instruction: R type, load, the memory type, the load, and then BQ. Then another question: how about the store? The same. Store word X1, X2, and immediate. So branch is obviously 0. How about the mem read is also obviously 0 because this is the store instruction. Okay. Mem to reg, the store instructions, actually this is the source register, right? So store instructions does not update store instruction does not update register file. So mem to reg is don't care, right? ALOP00, that's what we learn. Mem right? Obviously 1, because store instructions update data memory, right? ALU source is 1 because we need to check performs the immediate plus X, the source register 1. Regulate 0, right? Because store instructions update the data memory, not registers. So regulate is 0. So if we understand the behavior of instructions, then we can define the control signals, right? And then we can just check the opcode field of an instruction, right? Okay, that's it. This is the completed design. So, and then this is the CPU. So which means that our CPU can execute the RISC-V instructions. Wow, great. Okay. So for the functional part, so this CPU is okay. So which means we can design the CPU, and then this CPU can support the defined RISC-V instructions, right? This is okay. The functionally it's okay, right? But so actually, so we need also focus on the performance of computer systems, right? That, and then I explained that's why we are learning about the computer engineering or computer science, right? We can just focus on the performance. Actually, we need to we need to focus on the performance of our target computer systems, also cost. So these are two important factors for our research or our study. Okay, coding, it's just the language. So we can write, we can build some applications, but it's just language. It's just as a computer engineering student or a computer science student, we need to focus on the performance and cost of the target systems, right? Target systems also includes the application, operating system, hardware, right? So it's okay. This CPU is functionally okay. So which means in chapter 2, we learned about the CPU model. So CPU receives the instruction and then CPU generate the defined outputs, right? It's okay, functionally okay, but performance issues. Why? Why? So this is the single cycle CPU, which means within a single clock period, this is the TC, right? TC, this CPU needs to complete the required operations for an instruction, right? And then what are required operations? So, for example, load instruction, because the load instruction, the delay of load instruction is the longest, right? So for load instruction, the PC needs to be set, and then we need to fetch instruction from the instruction memory, and then we need to read data from register file, and then using the ALU, we need to generate the address of a load instruction, and then using the load address, we need to access the data memory, and then the read data is written back to the register file. So I explained the required operations for load instruction. And actually, in order to use this data path element, the delay, we can observe the delay because this is hardware. And as I mentioned, if the input is given to this hardware, the combination and logic, after some delay, then we can get output, right? What does it mean? PC has the delay. Also, the instruction memory has the delay. Register read has the delay. Also the ALU has the delay. Data memory has a delay. Also, this, so in order to write the data, also it has the delay. So what does that mean? In order to perform the load instruction within one cycle, then we need to add all delays from all data path elements. Okay, so for the load instruction, we need to, for example, we need to add the delay of PC, delay of instruction memory, and then it's a plus a delay of register read plus the delay of ALU plus delay of data memory and blah 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 blah. So all delays need to be accumulated for calculating the delay of load instruction. And then this sum of delay needs to be smaller than the TC, right? So in order to design the system, the clock period of the system needs to be larger than the critical path delay. And then we define we figure out the critical path of this single site CPU. 끝나야 되겠네요. CPU is the load. What's the problem? In chapter 1, we learned about the execution, IC, CPI, TC. So TC is large. This means performance can be low. So single cycle processor, because in a single cycle processor design, we need to accumulate all delays of database element, and then this delay is very long. Then which means we need to use the very slow clock. Very slow clock means that the clock period is very high. So performance is low. So we need to improve the performance by using pipeline. So this is actually, as I mentioned, this is the very important topic in this course, pipeline. Okay. So in the next class, we will learn about the pipeline. Right? Okay, thank you for attention. Enjoy the holidays.